And I know it's a little bit of going to be a little bit of a pain to ask questions in this format, but I really do want you to ask questions. So like as usual, I want this to be a kind of accessible seminar. And so if you don't understand something, that's my fault, and you should stop me and let me know so I can explain it. All right, so since it's a little bit after 3:30, let's get started. Before we get started with the math, are there any last questions about the format? And welcome to all of you who are not from UGA. It's really nice to have such a big group. All right, so I'm going to wait a few seconds, and if there's no questions, then I'll begin. All right, let's get started. So let me start by introducing the setup for Deligne's finiteness theorem, and then I'll talk a little bit about the context. So suppose we're given X, which is a smooth variety over K, which is a finite field with Q elements. And suppose, moreover, we're given a geometric point in X, so that means a K bar valued point for now. Then to this data, one can associate a fundamental group. So that's called the étale fundamental group of X based at the space point X bar. And you're supposed to think it's like if you had a complex variety, you can take the group of loops in that variety based at your point up to homotopy. Well, that doesn't make sense in algebraic geometry. So instead what this is it's an algebraic analog. So it's a profinite group. And the defining property it has is that the category of continuous finite pi1 sets, so that means finite sets with a continuous action of pi1, and it's profinite, so pi1 is a topological group. Well, the category of such things is canonically equivalent to the category of finite étale covers of X. So this is we're trying to define covering spaces. We're trying to define the fundamental group using covering spaces. So this equivalence of categories is supposed to capture the relationship between the fundamental group and covering spaces. On the right-hand side, you have covering spaces, and on the left-hand side, you have sets with an action of pi1. So I've told you there's some abstract equivalence of categories, and writing it down in this case is very easy. So suppose you're given a finite étale cover y to x. Well, where does it go to on the left-hand side? It goes to the fiber over x bar, and that's a finite set. And then the claim is that that fiber obtains canonically the action, a continuous action of pi1. All right. So what is the structure of this group? We don't know much about it. It's actually very mysterious, but let me tell you a bit about it. So what are we given? We're given X, and inside of X, we have this geometric point X bar, and X maps to spec K, the point, and so of course X bar also maps to spec K. So this is a map of pointed varieties, and pi1 is functorial. So from this data, we get a map of fundamental groups, which I'll start writing a little bit lower. So we have the étale fundamental group of X, the thing we're studying, and that maps to the étale fundamental group of the point with this base point X bar. And it turns out this map is surjective. Okay, so let's figure out what this map pi1 of the point is. Well, it's something, it's a group which classifies finite étale covers of the point, so finite separable extensions of K. So does anyone in the audience want to type into chat what they think such a thing might be? So what's a group that which classifies finite separable extensions of a field? So my hint is to think about the fundamental theorem of Galois theory. Yeah, so Amelia writes automorphism group which leaves the base field fixed. So that's great. So the automorphism group of what? Well, it's the absolute Galois group of K bar over K. Okay, in this case, we're over a finite field. So what's the Galois group of a finite field? It's Z hat, the profinite completion of Z. Okay, so we understand this quotient group very well because we're over a finite field. So I claim we also understand the kernel of this map reasonably well. So it's the étal pi1 of x base changed to k bar, the coefficients in x bar, and this map is injective. So you're supposed to think that from topology, you're supposed to think you have a fiber sequence where x maps to spec k, and then the fiber, the geometric fiber, in fact, it's xk bar, and that's supposed to give you a long exact sequence of homotopy groups. And this pi1 thing here is like the algebraic manifestation of that. Okay, so it turns out I've explained more or less what this last group is. It's the absolute Galois group of the ground field. The first group here is a little more complicated, but we do understand it relatively well. On the other hand, this middle group is very mysterious. So it's some extension of something we understand well by something we understand reasonably well. So for example, if x is a smooth proper curve over k, this first group looks a lot like the fundamental group of a surface of genus G. It's at least its prime to L completion is the same as its prime to P completion is the same as the prime to P completion of the fundamental group of a surface. But this middle group is really mysterious, and it's this middle group which Deligne's theorem is about. So now I can state the theorem. So here's the main theorem I'm going to talk about, which is due to Deligne. And it says the following. It says the set of continuous, irreducible representations of this group, so rho from pi1 tall of x with our base point x bar into gln ql bar, so the algebraic closure of the L-adic numbers. Well, it almost says this is finite, so it's finite up to two things. So first of all, like if you have a representation, you can conjugate it by a matrix and you get another representation. So we really only want to look at representations up to conjugacy or up to isomorphism. And now second, this group we're studying has a quotient which is just z hat. And z hat has lots of characters. So we're going to also quotient out by twisting by characters of that quotient group. Okay, and the theorem is that the set of representations up to isomorphism and up to twisting by characters is finite. Okay, so that's not quite true. So we need one more condition, which I'll explain now. So it's a finite if we impose the condition that there's bounded wild ramification. And if you don't know what that means, that's okay. I'm going to explain in a second. At infinity, okay. And it's this set, the set of representations with bounded wild ramification, which is finite, as long as L is not equal to the characteristic of the ground field. All right, and Cheng Ho asks if twist is the same as precomposition. So not quite. So what twist means is that if we have a character of z hat, so a one-dimensional representation, we can pull it back to get a one-dimensional representation of this thing, and then we can tensor with any representation with that one-dimensional representation. So another way of stating this theorem, which I'll use later, is it's saying that the set of representations of the étal fundamental group of x, so this middle thing, of xk bar, this top thing, which extend to representations of this middle thing and have bounded wild ramification and are continuous. And the claim is that that set is finite. So does that answer your question, Cheng Ho? Okay, great. Okay, so let me say a corollary, which is a little easier to understand. So here's a corollary. So suppose x is smooth and proper. So there's no notion of being at infinity. There's no boundary. So then this bounded wild ramification condition goes away. So it says the set of continuous irreps rho from pi1 étal of x to gln QL bar mod conjugacy and twist by characters of the absolute Galois group of the ground field is just finite. And again, we impose the condition that L is not equal to the characteristic of the ground field. All right, so today I'm just going to prove the corollary. And I would say the proof of the corollary captures about half of the main ideas in this paper of Esnault and Kerz and in Deligne's original proof. So dealing with the wild ramification in the case of curves is fairly simple, and proving this theorem for non-proper curves is about the same complexity as proving it for proper curves. But dealing with bounded wild ramification, or even saying what that means for higher dimensional varieties, is really involved. So I'm not going to do it. Okay, so let me talk a little bit about, because I'm only going to prove this corollary, let me talk a little bit about this condition of bounded wild ramification and like what it means and why it's necessary. And then we're going to talk about the proof of this corollary, which is just the smooth proper case. All right. So first of all, let me just say what bounded wild ramification means. And this remark is for experts. And then I'm going to give an example which shows you some kind of condition like it is necessary, and that should be understandable to non-experts. So what does bounded wild ramification mean? So if the dimension of x is 1, so if you have a curve, this condition on bounded wild ramification means bounded Swan conductor. So if you'd like to know what Swan conductor means, you can go on Wikipedia and look it up. It's really complicated, and talking about it would take about the same length as giving this entire talk if I was to do it in any detail, which is why I'm going to focus on the case where it doesn't matter, namely the case where x is proper. But what I can do is I can explain why we need some condition like this. So let me give you an example, and it'll show you that these fundamental groups are a little weird in characteristic P. So I think this example is interesting. And if you take anything away from this talk, if you've never thought about fundamental groups in characteristic P, hopefully you'll find this interesting. So the example is, let's take X to be the affine line over FP. Okay, then the claim is that there exist infinitely many continuous representations from pi1 of the affine line to GL1 of QL bar. So that's just QL bar cross. Okay, and this is even up to twist. So this tells us two things. So first of all, you need some condition, right? Like this would contradict the theorem if we didn't have this condition on bounded wild ramification. So something interesting has to be happening. So the other thing it's telling you is that the fundamental group of A1 is really big, which is maybe a little bit surprising over the complex numbers. The fundamental group of A1 is trivial, like the complex numbers are contractible. Okay, so let me prove this claim. So first, I claim it's enough to show, ETS stands for enough to show, that the set of continuous group homomorphisms from pi1 of A1 into FP is infinite. So why is that? So why is that? So if anyone wants to type it into chat, that would be great. So does anyone see why? All right, so I've waited 7 seconds, so I'll spoil the answer. So the reason why is that FP embeds inside of QL bar cross, right? Just as the pth roots of unity. So if you have a representation, a group homomorphism into FP, you can just compose it with this inclusion, and then you get a representation into QL bar cross. So okay, so let's compute this space of homomorphisms from pi1 of the affine line into FP. Well, it's just a general fact, and this is analogous to the Hurewicz theorem, that this space of Homs is the same as H1 of A1 in the Étale topology with coefficients in FP. And there's a short reason why this is true. Well, Hom pi1 of A1 into FP classifies FP covers of A1, right? So things like y to the p minus y equals f of x. And so does H1. So H1 classifies torsors. A torsor for FP is just an FP cover. So it's enough to compute this thing. So the way you compute the cohomology of a sheaf is you try to put it in like an exact sequence of things you know. And there's an exact sequence of sheaves on the Étale topology of A1, which goes as follows. So it starts with the constant sheaf FP. That's the thing we're interested in. That maps to O A1. Well, because if you have a constant function, you can get a function out of it. And then I claim it's the kernel of the following map from A1 to itself, namely the map that sends a function on A1 is just a polynomial f, and we're going to take the map that sends f to the p minus f. Okay, so there's 2 questions. So first of all, why is FP the kernel of this map? Well, it's just because FP is exactly the fixed points of Frobenius. And if you're in the kernel of f to the p minus f, that means you're fixed by Frobenius. And the second question is, why is this map from the sheaf OA1 to OA1 surjective? And that's not obvious. So that's not true in the Zariski topology. That's not a surjective map of sheaves. But I'll leave it as an exercise to you. So a fun exercise, which you should definitely try to do if you haven't thought about this thing before, is to try to show that this is a surjective map of sheaves. And if you have trouble, you can ask me either after the talk or in my office hours tomorrow, which will also be on Zoom. Okay, so if you have a short exact sequence of sheaves, you get a long exact sequence of cohomology groups. And the interesting part looks like H0 of A1, with coefficients in O. That maps to H0 of A1 with coefficients in O. And that maps to H1 of A1 with coefficients in FP. That's the thing we're interested in. And that maps to H1 of A1 with coefficients in O. Okay, so can anyone tell me how to compute the cohomology of O, the Étale cohomology of O on the affine line? So you're going to have to use the following fact. Oh, so Raju has raised his hand. So Raju, you can unmute yourself and tell me the answer if you'd like.
Yeah, sorry. This was actually just a test to make sure this works. So can you hear me?
Yeah. Great.
Yeah. No, I mean it's because it's the same as coherent cohomology.
Yeah. So why is it the same as coherent cohomology? So Raju claims that HI of A1 with the Étale cohomology with coefficient in O is the same as HI of A1 now in the Zariski site, with the Zariski topology with coefficients in O. And why is that? You're right.
Thinking. I want to say descent, but that's not a full answer. I don't know.
That's exactly right. So it's because of Étale descent. And I'll kind of fill in if it's all right, Raju, I'll fill in why that's enough. Yeah, so the Étale descent says that if you have a coherent sheaf, whatever that means on the Étale site, then you get one on the Zariski site. And vice versa, you can just pull back. right? So that means there's an equivalence of categories between coherent sheaves in the two sites, but cohomology just depends on the category of sheaves. So does that help, Raju?
Yeah, perfect.
Okay, great. So can anyone tell me what H1 of O is on the affine line? So it's the same in the, it's 0. Yeah, that's right. And that's because the affine line is affine. It's in the name. And H0 is just K adjoint T, the functions. That's the global sections. And this is K adjoint T. So, okay, so we've written the thing we're interested in, H1 of A1 with coefficients in FP. And remember, this is just the same as the set of representations into FP, is the co-kernel of the following map, the map from K adjoint T to K adjoint T that sends a polynomial F to F to the P minus F. Okay, and then the exercise you should do. So not only is this not finite, it's not even finitely generated as an abelian group. Okay, and that implies something pretty cool. It implies that pi1 of A1 itself is not finitely generated. Because if it was finitely generated, then the set of maps into FP would in fact be finite. So that's pretty cool. So I mean, I think there's some, let me just give you a warning. I think there's some like tendency to feel like maybe pi1 and characteristic P is really pathological. And I actually think we should try to resist that urge to label it like that. Like it still really is meaningful. It's still something capturing something about Intel covers, and you can still prove a lot of stuff like about it and using it. Okay, so for the rest of the talk, I want to return to Deligne's finiteness theorem and let me remind you what we're going to prove today. So it's this corollary, which I will kind of point to using this box. So this corollary, which is the set of representations of pi1 of a smooth proper thing up to conjugacy and twist by characters of Galois, is finite. So before moving on to the proof, I want to talk a little bit about the context. So this is like part of a really long list of amazing finiteness theorems for Galois groups and fundamental groups. So I think the first such theorem is like the Hermite-Minkowski theorem, which says that that there are finitely many extensions of Q with bounded discriminant. So that's saying something like there are finitely many covers which are ramified with some amount of badness. So that's some kind of finiteness for the Galois group of Q unramified away from some points. All right, so then the second piece of context I want to remind you of is a talk that happened at the very beginning of this seminar by Jimmy Dillies, which is also about a result of Deligne over the complex numbers. So Deligne showed that there are finitely many rank R Q local systems on a Riemann surface which underlie a polarizable variation of Hodge structure. Okay, and if you don't know what that means, that's okay. You should think it's some kind of Archimedean analog of being a representation of the arithmetic fundamental group. And we'll see later on that being a representation of the arithmetic fundamental group is really closely related to coming from geometry. Okay, and then finally, the last bit of context I want to mention is the Shafarevich conjecture, which was proven by Faltings as part of his proof of the Mordell conjecture, that there are finitely many rational points on curves of genus at least 2. And what Faltings proved is that there are finitely many, well, one way to say it is that there are finitely many principally polarized abelian varieties of a given dimension with good reduction outside S, where S is a set of places of a global field. Okay, and so if you think about that a little bit, it's like an abelian variety is very closely related to the Galois representation on its tape module, and it's very faultiness is also shown finiteness results for sort of representations that can arise from geometry like this. So you're supposed to think is this Shafer-Abich conjecture is maybe some kind of geometric analog over number fields of the results we're talking about today. All right, so with that, I hope that motivates the result a little bit. I mean, I think it's saying something. The result we're going to talk about, this finiteness theorem, is saying something really beautiful and fundamental about fundamental groups. But I do want to make it clear that it's part of a bigger picture. All right, so with that, I'm going to start explaining how to prove this finiteness result in the smooth proper case. So before I do that, are there any questions? All right, great. So let me remind you what we're trying to prove. So X is smooth and proper over K, which is a finite field FQ, and L is a prime which does not divide Q. So we're trying to show that the fundamental group of X has only finitely many representations, irreducible representations into GL and QL bar, up to conjugacy and up to twist. So let me scroll up and show you that. So this corollary at the top of the page is what we were trying to prove. So the set of continuous irreducible representations from pi1 into GL and QL bar up to conjugacy and twist is finite. All right, so my first claim is that we can immediately reduce to the case that the dimension of X is 1. So we're working with a smooth proper curve. So why is that? Well, the proof is that for any smooth ample curve, so any like complete intersection of ample divisors in X, C and X, there's a map. Well, C is an X. So the étale fundamental group of C maps to the étale fundamental group of X, and this map is surjective. Okay, and that's called the Lefschetz hyperplane theorem, or it's part of the Lefschetz hyperplane theorem. For pi1, which you can find in SGA2. All right, so if we've proven a finiteness theorem for representations of C, that immediately implies one for representations of pi1x, because if you have a rep of pi1x, you get one of C. Great. So here's a puzzle for you. Why are there any smooth ample curves in X? Like, why can we actually find a curve like this? Okay, Raju, go ahead.
I mean, this just follows from Punin's Bertini theorem, I guess.
Yeah, so the key is you have to say something a little bit more than a Bertini theorem, and you said it. You said Punin's Bertini theorem. So what would we do if we were over the complex numbers? We'd like take some very ample divisor or some very ample line bundle, and then we'd cut by hyperplane bisections to that line bundle until we had a curve, and we'd know from Bertini that for a generic way of doing that, we'd get something smooth. So over a finite field, generic doesn't cut it because there's only finitely many sections to a given line bundle because we're over a finite field. We have an FP vector space. So it's possible that none of them are generic enough. So you could, like Raju said, use Bertini's theorem, or if you were a little lazier, you should sort of use Punin's Bertini theorem, or if you were a little lazier, you could just pass to a finite extension of K where a generic section actually exists. Oh, but that's the proof. So now what do we want to prove? So now we're in the case of a curve, and we want to prove the following. So suppose C is a smooth, proper, geometrically connected curve over K, which is the finite field FQ, and L is a prime which doesn't divide the characteristic of K, so it doesn't divide Q, then we want to show that the set of continuous irreps rho from pi1 of C now to GLN QL bar, and here n is fixed, mod conjugacy and twist by characters of the absolute Galois group. So this is some set, and we want to show that the set is finite. Okay, so there are, I think, two proofs of this fact. So both of them, so all known proofs, use Laforgue's work on the Langlands program. Langlands for function fields. So as far as I know, there are two proofs. So one of them just says, and if you don't know anything about Langlands, that's okay. I'll tell you what you need to know. But at least part of the Langlands program tells us that there's some kind of bijection between representations of these groups and automorphic representations. And so we can equivalently phrase this as a finiteness theorem for automorphic representations, which is known. So this proof uses finiteness for automorphic representations. And I don't know a lot about automorphic representations, but my understanding is that such finiteness theorems are maybe not incredibly hard, although they're certainly not trivial. Okay, so the proof we're going to give today is a different proof, which as far as I know is actually not in the literature. It's sort of only alluded to in a remark of this Esnault and Kerz paper, and it's a proof via sphere packing. Okay, and the idea of this proof is to imitate character theory for finite groups. All right, so that's what I'm going to explain for the rest of the talk. So before I start explaining it, are there any questions? All right. So I guess this is, let's start. So let's just start with the case of rank 1, which is supposed to be easy. So in this case, we're trying to understand Hom pi1 into QL bar cross, right? So conjugacy is a trivial condition because this is an abelian group. So we just want to understand this up to twist by characters of the absolute Galois group. All right. Well, I claim this is the same as Hom from the abelianization of pi1 into QL bar cross modulo twist. Why is that? Well, it's because QL bar cross is abelian. And does anyone know what that abelianization is? It has another description. Maybe in terms of the Jacobian of our curve. Someone has drawn an arrow. Oh, that's all right, Michael. All right, so I claim this abelianization is just the Tate module, and this is something that comes from sorry, this is a little tricky. So another way of writing this maybe is I'll say this is the same as Hom from pi1 of the abelianization of pi1 of CK bar into QL bar cross. and the Frobenius fixed things, or the Galois fixed things. And now maybe it's easier to describe this pi1 of the abelianization of pi1 of ck bar. So that I claim is just the Tate module of the Jacobian. Sorry. It's total Tate module of the Jacobian of C. And we're looking at the Galois fixed parts of that. Okay, so can anyone give me a different description of that? So you have to do some unwinding, but it turns out this is the same as Hom of the co-invariance of Galois, so the co-kernel of Frobenius minus the identity on the Tate module into QL bar cross. And this co-invariant group has another name. So has anyone seen this before? So I claim this is actually just the set of rational points of the Jacobian. So, okay, so can anyone tell me, are we done? So what do we know about the set of rational points of the Jacobian of a curve over a finite field? Yeah, it's finite. Zach is right. So this is a finite group. So now we're looking at the set of characters of a finite group, and there are finitely many of those. So we win in the rank 1 case. Great. Okay, so this there's a lot of equalities here that I haven't justified, and I won't. And so you should, as an exercise, try to justify all these equalities of Homs. And if you can't, you should ask me after the talk or come to my office hours tomorrow. Okay, so now let's get to the character theory. So that was the one-dimensional case. So now let's talk about the rank bigger than 1 case. So I'm going to define some kind of character associated to any representation. So let's say given a representation rho from pi1 of C into GLN, or let's say GLR actually, GLR QL bar, we're going to define the following. The character, and there will be one for each integer n, will be a function from the fq to the n rational points of our curve C to QL bar. And what it'll be, well, if we have a point of a curve valued in fq to the n, that's a map from spec fq to the n to C, right? So if you take the image of the Frobenius under that map, you get an element of pi1 of C, which is called the Frobenius at x. And what are we going to do? We're going to send our point x to the trace of Frobenius at x. So that's some element, or really some conjugacy class in pi1 of C, acting on rho. Okay, so this is just like some kind of character, right? We have a bunch of special elements of pi1 of C, namely the Frobenii at the closed points of C. And we're taking the traces of those special elements acting on our representations. And we're going to try to imitate character theory with this this construction. Okay, so what do we know about these traces? Okay, so first of all, we know the following fact. So this is a corollary of the rank 1 case. So we know that some twist of rho has determinant of finite order. Okay, and this is going to be, we're about to use Deligne's program, but before we do that, let me explain why we know this. So in this rank 1 case, we proved that any rank 1 representation has finite image when you restrict to pi1 of C K bar. So what that means is that any infinite image in the determinant has to come from the Galois group of the ground field, and we can just twist that away. So we know that some twist of rho has determinant of finite order, and now we're going to use that. So from now on, I'll always assume I'm working with such a twist. And we'll use the following fact, which is due to Laford. So this is a corollary of his work on the Langlands program for function fields. So any irreducible row with determinant of finite order, so that just means the determinant has finite image, has weight 0. So what does that mean? So that means that the eigenvalues of frob x, so the Frobenius I at these points x, for here x in any fq to the n point of C, are, well, first, they're algebraic numbers. And second, they're not just any algebraic numbers, they're really special algebraic numbers. So for any iota, well, that's going to be a map from Q bar into C. And here we're going to view Q bar as living inside of QL bar, right? Because these eigenvalues a priori just start as algebraic numbers inside of QL bar. So for any embedding of Q bar into C, what we know is that iota of these alpha I has absolute value 1. Okay, this is really not obvious. I mean, even the fact that these numbers are algebraic numbers is really not obvious. So maybe it's worth remarking, I mean, this is a corollary of a much stronger thing Laford proves, namely that rho kind of comes from geometry. So it comes from the cohomology of a family of varieties over C. Right. Okay, great. So now what that tells us, so the corollary is that these chi rho n's, well, we said they were maps from C fq to the n into QL bar, but they actually factor through Q bar. Because if the traces of our Frobenius are algebraic numbers, or sorry, if the eigenvalues are algebraic numbers, so are the traces. Okay. And from now on, I want to use the complex numbers. So I'm going to fix some embedding iota of Q bar into C. And here I'm thinking of Q bar as the algebraic numbers inside of QL bar. Okay, so the idea of what we're going to do is we're going to try to prove kind of orthogonality relations. For the chi rho n's. And that makes sense because we've now viewed them as functions into C, so we can do things like use the standard inner product on C to the n. And that's what we're going to do. Okay. So that takes us to section 3 of the talk, which is about orthogonality relations. So before I begin with that part of the talk, are there any questions about the general strategy? Or about anything that's come up in the talk so far? All right, then let's keep going. So let me just remind you, I'm not really defining this, I guess you've all seen this. Let me remind you what the standard inner product is on C to the n. So I'm going to view it as an inner product on C to the number of points, to the set of points in fq to the n, fq to the n points of our curve. Okay, so these are functions valued on the point of the curve into C, and the chi rho n's are examples of such things. Well, what is it? So given two functions from the points of our curve to the complex numbers, f and g, I'm going to define their inner product to be the sum over, over the fq to the n points of our curve of f of x times g of x bar. Okay, so what we want to show, what we're going to show if we want to try to imitate the orthogonality relations for characters, is that if we take two characters and take their inner product, well, that'll be big if they're the same and small if the characters are different. So if we can do that, we win, because like we have a bunch of vectors in a finite dimensional vector space. They all maybe lie in the unit ball and have big angles between them. And so that's what Deligne means by sphere packing. He means you can only fit finitely many vectors on the unit ball with big angles between them. Okay, so in order to do that, we're going to have to interpret this inner product. So we need some kind of interpretation of the inner product of two of these characters, chi rho 1n and chi rho 2n. Okay, so what is this? Well, just by definition, this is the sum over the points of our curve of the trace of Frobenius at our point on row 1 times the trace of Frobenius at our point on row 2 conjugate. Okay, and I think this conjugate should scare you, right? Because this conjugate used this like random embedding we chose of Q bar into C. So this thing is very mysterious. Like it's not clear, I think, from the point of view of QL bar representations, how to interpret this. So in order to interpret this, we're going to have to use Lefort's work again. So here's another fact, which is again a corollary of the Langland's program, or Lefort's work on the Langland's program, and this fact is called sigma companions. Okay, and so here's the theorem, or that Lefort proves. So suppose rho is a continuous rep of pi 1c of weight 0, and sigma is an automorphism of Q bar. So then Lefort proves that there exists some rho sigma such that for all n and for all points in our curve valued in fq to the n, if we take sigma and apply it to the trace of Frobenius at our point on rho, that's the same as the trace of Frobenius at our point acting on rho sigma. So this gives us a way of interpreting this sort of trace, these sort of conjugate traces. They come from some other interesting representation. So let me say a word about why this fact is true that Lefort proves. So in fact, Lefort proves that any weight 0, sorry, this should be a continuous irrep for it to be true. So Lefort proves that any continuous irrep of weight 0 comes from geometry. And things which come from geometry are direct subends of things where the Frobenius traces are defined over Q. So what that means is they break into pieces which are Galois conjugate to each other. So that's somehow the origin of this fact proved by Lefort. Okay. So now back to our situation. So if sigma is complex conjugation, so meaning coming from our embedding into Q bar into C, I'm going to write rho bar for rho sigma. Okay, so now we can try to interpret this mysterious sum from before. So let's do it. So then the thing we're trying to understand, chi rho 1n interproducted with chi rho 2n is, well, remember just the definition was the sum over the fq to the n points of x of the trace of Frobenius on row 1 times the complex conjugate of the trace of Frobenius on row 2. And what we've just learned is that that's, sorry, complex conjugate. What we just learned is that that second thing has an interpretation. So it's the same sum, except we can think of it as the trace of Frobenius acting on row 1 times the trace of Frobenius acting on row 2 conjugate. Okay. Well, what's a product of traces? It's the trace of the tensor product, right? So that's the same as the sum of the points in f q to the n of the trace of Frobenius acting on row 1 tensor, row 2 bar. Okay, and now I'm going to do one more simplification. So if you see a sum of traces, or in general, if you see a sum of traces over fixed points, so f q to the n, sorry, these should be frob to the n's everywhere. I'm sorry about that. So the frob to the n fixed points of cfq to the n are, well, okay, and maybe let me just call them frob because I'm working over. It's the Frobenius of fq to the n. So the fixed points of frob are the fq to the n points of c, and if you see a sum over fixed points, you should think the Lefschetz trace formula. So now I'm going to apply the Grothendieck Lefschetz trace formula, and we get this is the sum from I equals 0 to 2. Well, why? Because the curve is cohomological dimension 2 of -1 to the I times the trace of Frobenius. It's now the absolute Frobenius, acting on the compactly supported cohomology of CK bar with coefficients in row 1 tensor, row 2 bar. Okay, so if you haven't seen this before, don't worry about it. It's some étale cohomological version of the Lefschetz fixed point formula. Okay, so now this tells us something about the inner product. So now we're going to use that to try to prove some kind of orthogonality relation. And let me do it. And I'm just going to do it in a baby case. And then I'll indicate how you have to change it for the general case. So I'm going to prove finiteness. So the same finiteness theorem as before for so-called conjugate self-dual reps. So that means reps such that row bar is isomorphic to row dual. All right, so let's prove that the set of irreducible conjugate self-dual reps is finite. So what kind of claim do we want to prove? We want to show that for row 1, row 2, conjugate self-dual, irreps, the inner product of the character of row 1 with the character of row 2 is, well, big if row 1 is isomorphic to row 2 and small otherwise. All right, so let's prove it. So here's the proof, and I'll say what big and small means in the course of the proof. So this inner product, we can just compute. Well, we computed it before. It's the sum from I equals 0 to 2 of -1 to the I times the trace of Frobenius on row 1 tensor, row 2 bar. Okay, but I assumed that the row i's were conjugate self-dual, right? So row 2 bar is row 2 dual. So let's write that. Okay, and this latter thing is just Homs from row 2 to row 1, right? So this is Hom from row. Oh, I'm sorry. There should be some cohomology groups here. I forgot the i's. You guys should feel free to point out if I'm making a silly mistake like that. Okay, so this is just this row 1 tensor row 2 dual is Hom from row 2 into row 1. Sorry, just the thing on the row. Okay, So now we're finally going to use like one of the most fundamental facts in arithmetic geometry, which is also due to Deligne in Bay 2. So row 1 and row 2 both have weight 0, because I assumed I'm always working with such things. The fact Deligne shows is that if you take HI, compact support, of CK bar, with coefficients in anything of weight 0, so in particular HOM from row 2 into row 1, this has weight I. So what does that mean? It means the eigenvalues of Frobenius live in Q bar and have absolute value Q to the I over 2. And this is for any embedding from Q bar into C. Okay, so now we have this sum of traces and we know something about the eigenvalues that show up. So how can we understand the sum? Well, the trace is going to be bounded in terms of the size of the eigenvalues times the number of eigenvalues, namely the dimension. So let's compute the dimension of HI compact support of CK bar with coefficients in this HOM from row 2 into row 1. Well, what is it? I claim it's 1 if I equals 0 or 2, and row 1 is isomorphic to row 2, and 0 if I equals 0 or 2, and row 1 is not isomorphic to row 2. So I equals 0, this is pretty easy. It's just saying that you have two representations. What are the maps between them? Well, if they're irreducible, there's one-dimensional space of map if they're the same, and a zero-dimensional space of maps otherwise. And so that's for I equals 0, and then, so this is like, that's like Schur's lemma. And then for I equals 2, you have to use Poincare duality. Okay, and then the dimension of H1, well, that's a little more mysterious. So I'll just tell you the answer. The way you compute it is you compute the Euler characteristic and then subtract off what you get for H2, and you end up getting 2 times the genus times n squared plus 2 times the delta function of row 1 and row 2. So from row 1 and row 2 are isomorphic, you add a 2, otherwise you don't. Okay, so now we win. So before explaining why we win, let me make one more remark. So in the non-proper case, so this is the only place things change. So this is the only place I've really used properness so far. So in the non-proper case, this dimension of H1 can be bigger. And you have to use something called the Grothendieck-Shafarevich formula to control it. And for experts in the room, that's where the Swan conductor comes in. Okay, so now I claim we win. So I claim what we get. So we know the dimensions of these vector spaces, and from this fact of Deligne, we know something about the eigenvalues of Frobenius. And if you put those together, you get that chi rho 1n, chi rho 2n is, well, it's q to the n plus O of q to the n over 2 if rho 1 is isomorphic to rho 2. And it's O of q to the n over 2 if rho 1 is not isomorphic to rho 2. Okay, and now let's prove finiteness. We're done, basically. So let's take, oh yeah, so the key fact here we also need is that the implicit constants here in the O's are bounded in terms of the rank of row and the genus. And that just comes from the dimension estimate for H1 above. Okay, so the proof of finiteness is we now have all these vectors. Their inner products are small unless they're the same, in which case they're big. So let's consider like 1 over q to the n times chi rho n. So these live inside of C to the set of rational points of Q. And we're going to take Q to be much bigger than the genus of our curve. So now we have these points. These are close to unit vectors, because their inner product with themselves, sorry, that should be Q to the n over 2. Because their inner product with themselves is 1, right? That's because BV is close to 1 by our estimate. And they're close to orthogonal. Because, well, VW is small. Okay, so we have a bunch of unit vectors which are close to orthogonal. So the picture is you have a bunch of things kind of near the unit ball, and the angle between any two of them is big. So now we're done by the finiteness. We have finiteness, and it follows from compactness of the unit sphere, for example. All right, so we win. So that did the conjugate self-dual case, and I'm out of time. So let me just say a word about the non-conjugate self-dual case. So in the non-conjugate self-dual case, we just add in to our set of reps that we're thinking about, rho direct sum, rho bar dual. So this thing isn't irreducible, but it is conjugate self-dual by definition. Okay, and a few things will change. So some of the estimates will change. In particular, you'll see a 2q to the n somewhere instead of a q to the n. So instead, you'll be kind of doing the sphere packing. Instead of being on the unit sphere, you'll be on an ellipsoid. But the rest of the argument is basically the same. All right, so I think that's all I wanted to talk about today. Maybe if we have time later in the semester, I'll try to talk about how to do the higher dimensional case, like how to deduce it from this case. There are new ideas required. But with that, let me end things. So do any of you have any questions? And it's fine to raise your hand to ask them or to type into chat. Oh, Chang Ho writes clap. Thank you. Yeah, I think there may even be a clap button on the, oh yeah, multiple people are clapping. Thank you, Amelia. All right, thank you guys for clapping. So Santana has raised his hand. So Santana, feel free to unmute yourself and ask a question.
This, like how big it is, or is any other like what it looks like as the automorphism group of pi1 acts on these representations?
Sorry, can you say that again? I had a little bit of trouble hearing you.
Are there any results on the bounds of the set?
Oh, like how big this finite set is? That's a great question. So there are. It's a really interesting result. So this proof is effective, right? So it gives you a bunch of vectors in some complex vector space of bounded dimension, and it says they're almost all, or they're kind of all almost orthogonal to each other, and you could use that to come up with a bound. So that bound is, I think it's actually on the right order of magnitude, but in fact we know much more. So they're really amazing results of Deligne and Flicker, which I think and others, but I think the complete story is not quite known, even in the proper case maybe, where they count reps of pi1 of a curve, and they look at like your curve over your finite field, and they look at bigger and bigger extension fields. So as you do this, there are more and more representations as you make fq to the n bigger and bigger. And the really amazing thing is that the generating function looks like the zeta function of a variety over a finite field. So this number, the number of reps of pi1 of CFQ to the n, like has a generating function. Which is rational. And the zeros and poles of that rational function are Cuvier numbers. So that means they're algebraic numbers whose absolute values are powers of, whose absolute values are powers of square root Q. So it's really incredible. The only known proof uses automorphic methods, so they explicitly count automorphic representations. And I think it's still kind of very mysterious from the point of view of what we're talking about today. So just looking at the Étale fundamental group directly. Does that answer your question, Santana?
Yeah, that was great. Thank you.
Great. Anyone else have any questions? All right, so Michael asks on chat, are you going to post a PDF of these notes on the CRAAG webpage? I can if you'd like. They're a little messy. I have much cleaner notes that I've handwritten and have been working from during the talk, which I might post, but I actually have been recording this, and if no one objects, let's say in the next minute, I'm going to post the recording. So, okay, and Santana gives me a thumbs up. All right, so Binglin asks, what's the key insight for the higher dimensional case that's different from the curve case? That's a great question. So, okay, so we proved actually part of the higher dimensional case today, right? We proved the higher dimensional case for smooth projective varieties. So the question is like, what do you do in the quasi-projective case? And let me scroll up to how we used projectivity. So we used it. So we used it here, where we used the Lefschetz hyperplane theorem, right over here. So it's not obvious, but in fact, it's true that for lots of quasi-projective varieties of dimension bigger than 1, there's no curve whose pi1 surjects onto pi1 of the variety. So for example, if you take A2, there's no curve in A2 whose pi1 surjects onto pi1 of A2. So you're not going to be able to directly reduce to curves. And so the question is, like, how do you actually reduce to curves? And that's Deligne's insight. And Deligne uses these techniques called space filling curves. It's really, it's a little too complicated to try to summarize in a 2-minute answer to a question. But if you guys are interested, we can talk about it in my office hours tomorrow, or I can give another talk about it at some point. But yeah, the idea is, I mean, in fact, many of these estimates we've used go over in the higher dimensional case, and somehow those can be used to find some maybe very large collection of curves in our variety, which control all the representations with bounded wild ramification. But I actually think there are a lot of interesting open questions around here, around this issue. So for example, I think it would be interesting, and I think probably doable, to try to define a fundamental group of a quasi-projective variety with bounded wild ramification, and then to try to prove a Lefschetz hyperplane theorem for such a group. And that sounds kind of plausible to me, that such a thing might exist. I don't think anyone has done it. Does that answer your question, Binglin? Yeah, and and Binglin asks when I'll have office hours, so let me remark on that. So I'll actually write it down. So my office hours are going to be every, office hours will be every Friday from 2 to 4 p.m. EST, at least for the next few weeks, and they'll be on Zoom. And even if you're not a student at UGA, you're welcome to attend. We'll be discussing like arithmetic geometry stuff, but also you can ask about like career stuff or, you know, whatever issues arise. So to find the link, I've tweeted it out, but I'm also going to post it on my webpage. And if you email me, I'll send it to you also. Great. All right. Any more questions?